Okay, today what I want to do is talk about the Kalman filter. So this is going to be a multi-part series video, and this video is just going to be on the overview. I'm not really going to do any equations or anything like that. I'm just going to talk about what it is and how it works. Okay. So the idea is that as time progresses, you're going to have, say, the truth variable x is going to have some initial condition. Okay. And if we assume that the state equations, they can be completely nonlinear, they can be in a fine form, it really doesn't matter. If we just assume that those are the perfect dynamics, and there's no, well, let's just say that there's some dynamic equation that we can model using analytic equations, and we don't necessarily know what that is. Well, as this system propagates through, it's going to, follow through some time series. And understand that this, I'm drawing this one-dimensional, but this x vector here is an n-dimensional vector, and so this is an n by 1. And so you might have n by 1 states that you are trying to estimate, okay? You're going to have an output equation where y is h of x, okay? And let's just again assume it's linear. Y is h of x times x. And this is going to be, your output equation is going to be m by 1, and so this h here then obviously is an m by n matrix, okay? And so m is a number of measurements, and n is the number of state equations, okay? So the idea is what I want to estimate x based on my measurements y. And what I'm going to do to denote my measurements is I'm going to draw a bar over it. And what I'm going to do is I'm going to assume that, I'm just going to say y bar is my measurement there. Okay, so I've made a measurement and I've sort of gone and get there. These are sort of the truth equations. And I may not know what f, g, or h is. I might have an estimate of it, but I might not actually know what it is. But let's just assume, for the sake of the argument right now, that there is those truth equations, and this system propagates through, okay? Well, the world doesn't work like that, obviously, right? So at the initial condition, you're going to have a measurement, call it x naught, you're going to have a measurement called y bar naught. It's going to be your initial measurement, and you're going to need to use a model, right? You need to assume some model. There needs to be a vector across that. Okay, and so basically you're going to have some measurement y, which has this state here. And you're obviously going to have some measurement noise v, right? It's not going to be perfect, okay? And you're going to use this equation somehow, and I'll show that in another video. And basically what you want to do is you want to do some least squares estimation. And you're going to estimate your initial x tilde 0, okay? And you're going to have some error between these two, delta x, right? But, for the sake of the argument, let's just say that, we're going to have a little bit of error and we'll worry about it later, okay? Now, you don't actually know what these equations are here, right? So not only is your measurement a little bit off, but if you created some estimate equations, I'm assuming that my input, because I'm the one sending the command, I know what u is. So it's not an estimate because the controller is computing the input, and whether or not it's getting passed to the state correctly is a completely separate issue. That kind of gets absorbed into this g tilde. But these are sort of my model equations, okay? Now, because my initial condition was wrong and my model is wrong, right? This is going to propagate differently than this equation here, right? So keep in mind I've got measurement noise here, measurement noise, I also have model noise. And the way to model that is I can say, take my x tilde dot, and I'm going to assume, so that the math is easier, that it's really just like this. It's actually the truth equations plus some model noise. Now this here, this model noise, you have to look at it, not only is it an n by 1, but it's also a function of time. So it's time dependent, it might be correlated, I might have some white noise in it, some colored noise, it could have a lot of things. And so, when you go from here to here, you add this term, don't think that's like, oh, okay, all I need to do is subtract this and everything's all well and good. You still have this model noise here it's almost chaos in a way, right? The point is, though, is that if you integrate either of these equations, you're going to drift quite considerably, right? And you might even shoot off to infinity, okay? And so if you just take your initial condition and integrate, even if you had a perfect measurement, because your model is incorrect, you're going to get pretty significantly far away from your actual truth signal. So the idea is that when at some specific interval, let me do a different color here, let's get green. At some specific interval, this will be your delta t measurement update. I'm going to get a new measurement y bar, okay? So every delta t seconds that goes by, I'm going to get a new measurement. I would hope, and the Kalman filter doesn't work if you have a lot of model noise and a lot of sensor noise. You either need to have a really, really good model and bad sensors, or really, really good sensors and bad model. In this case, I have a pretty bad model. So let's assume that my sensor measurement is here. Now keep in mind, I get y bar, and I need to do some linear least squares to estimate my x. And I also have to take into account a priori knowledge of the state, but again, that'll be in separate videos. But the idea is I get this new sensor measurement here. So the issue that you have is that you have a estimate of the state, x tilde k, right? So this is the kth measurement update. So I'm going to call this y bar k. As you integrate, you're going to have an estimate of the state here, and you're also going to get what I'm going to call x tilde, I'm going to call this xk plus 1. I'm going to call this xk minus, okay? And then this is xk. Okay? So basically what's going to happen is that you have your x tilde naught, and you're going to integrate these model equations forward, and you're going to get an estimate of the state, what I call minus, which means right before the Kalman update, okay? And so the question that you have to ask yourself is, which do I believe, okay? And so what you have is, do I believe xk minus, which, that's my model estimate, or do I believe xk tilde, which is my my new sensor measurement. It's my estimate from my sensor. Okay? And which one do I believe? And again, I was saying before that depending on your Kalman filter, you have model noise and measurement noise. One of these needs to be better than the other. And you need to sort of make an estimate as to which one of these is better. Do you have really low measurement noise, in which case you want to believe your measurement? Or do you have really low model noise, in which case you want to believe your model? However you want to do it, you basically need to do a least squares update between the two. If you perfectly believe your new sensor measurement, you're immediately going to pop up and then start integrating from here. If you believe your model, you're just going to keep, integrating from there. typically what happens is that you take sort of the best of both worlds and you do sort of a weighted update based on how bad your model is and then how bad your sensor measurements are. And so typically what's going to happen is you're going to jump to, say, if you're doing the complementary filter, you're going to jump halfway. Okay? So then you integrate again and you're going to deviate, and then you're going to go to a new measurement update. So this is measurement update of y, k plus 1. And then again, you have your estimate of the state based on your model, k plus 1. And then you also have your new measurement up here. I'm going to say, well, let's assume it's a little bit below this time because it's random. And this is your new, this is xk plus 1 tilde, which is from your sensor. And then again, you do the Kalman update and you repeat again and you say, again, I'm going to take this is the complementary filter route and I'm going to go halfway. And I'm going to go from there. Okay? And so basically you keep repeating this. You integrate your model equations, you make an update. You get a new sensor measurement, you make an update. You integrate your model equations, you get a new measurement, you make an update. You integrate your model equations and you just repeat over and over and over and over again. And so there's a lot of piece parts to this. First, you have linear least squares. And I will post a video on that after this. You're also going to have weighted least squares. And the reason why it's weighted is because you need to take into account your model and your measurement noise. You're also going to have sequential least squares. And the sequential part is that every time you get an update, you want to use the information from before. And so that's essentially saying, like, okay, I have sequential, but what about a priori knowledge of x? You know, what if I already have a measurement of x? And that's what's happening here, is I'm integrating and I already have a measurement and I get a new one. Can I use that previous knowledge to do that? And then finally, you get covariance and state propagation. And the idea is you are trying to integrate your covariance as well as your state. And if you put all 5 of those things together, you have a Kalman filter. Okay? A Kalman filter was invented by a guy named Rudolf Kalman back in the 50s or 60s. If I remember, if I had my facts correct, you can check me on Wikipedia, but I'm pretty sure that was his PhD thesis, and he did a derived the Kalman filter, and that was his PhD there. I gotta work on the posture here. So I guess I'm gonna make 5 videos on this, maybe 6. And we'll go from there, but this is the overview of Kalman filters. Cool? See you on the next video.